Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches of the outer solar system, where something unexpected has arrived. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On the 13th of January, 2025, a routine sky survey picks up a faint smudge of light near the orbital plane of Jupiter. The automated telescope, stationed atop a volcanic mountain on Mauna Loa, records the object's position, brightness, and motion across a field of stars that have not moved in any human lifetime. The software catalogs it provisionally. A number is assigned. Preliminary calculations begin. The machine does not know yet what it has found. It simply records, measures, archives. The telescope is part of a network designed to catch things that move, asteroids that might threaten Earth, comets returning from the outer system, debris shed from dead spacecraft. Most detections are familiar. Objects follow predictable paths, looping around the sun in ellipses carved by gravity over millions of years. The mathematics of orbital mechanics, refined since Newton, allow astronomers to predict where something will be months or years in advance, based on just a few nights of observation. Within hours, the orbit appears wrong. Not slightly eccentric, not mildly perturbed by a distant encounter with a gas giant, but fundamentally unbound. The trajectory bends through the solar system at an angle too steep, a velocity too high. Gravity holds planets in their grooves, asteroids in their belts, comets in their long elliptical loops that stretch toward the outer dark before curving back. This object refuses the loop entirely. The calculated eccentricity exceeds 1.0. In orbital mechanics, an eccentricity of exactly 1 describes a parabola, the boundary case, an object that just barely escapes. Anything higher describes a hyperbola, an open curve, a trajectory that passes through once and never returns. The visitor's eccentricity calculates out to approximately 1.2. It is not bound to the sun, it has come from somewhere else, from the space between stars, from a place where the sun's influence fades to nothing and the galaxy's slow tides take over, where stellar encounters occur once every few million years, where dust drifts in currents shaped by radiation pressure and the faint push of distant supernovae. From a region that no human mission has ever reached, that no probe will visit for centuries, if ever, only the third such object ever detected. The designation follows 3 Tseet Atlas. The I stands for Interstellar. The 3 places it in sequence after 1I, ʻOumuamua, discovered in 2017, and 2I Borisov, which arrived in 2019 and behaved precisely as expected, a textbook comet with a glowing coma and a beautiful tail, courteous enough to match every prediction. 3U Atlas will not be so cooperative. There is no drama in the announcement. Numbers are published in circulars distributed to observatories worldwide. Ephemerides are calculated tables predicting the object's position for every hour of every day as it crosses the inner solar system. Observers around the world adjust their instruments, reprogram their schedules, point billion-dollar mirrors toward a dot of light barely brighter than a 23rd magnitude star. For context, the faintest stars visible to the unaided human eye shine at around 6th magnitude. Each step up the magnitude scale represents a brightness decrease by a factor of roughly 2.5. At magnitude 23, 3Y Atlas is more than 10 million times dimmer than anything eyes alone can see. The object continues along its path, indifferent to the sudden attention, moving at roughly 33 kilometers per second relative to the solar system's center of mass, fast enough to escape, slow enough to measure, fast enough that it will traverse the inner solar system in a matter of months, not years, slow enough that its motion against the background stars can be detected with patient, repeated imaging. It crosses the plane where Earth orbits, though Earth itself is elsewhere, far along its own yearly circuit. The timing is coincidence. Had this visitor arrived 6 months earlier or later, it might have passed unnoticed. Too faint, too far from any telescope's scheduled sweep of that particular patch of sky, but it arrives now, dim but detectable, threading through the narrow window where automated surveys happen to be looking, and the questions begin immediately. What is it made of? Where did it originate? How long has it been traveling through interstellar space? What star system, if any, did it come from? And most pressing, most strange, why does it refuse to brighten? Comets are supposed to wake up as they approach the sun. This is fundamental. This is observed hundreds of times per year. Ice sublimates when warmed water ice, carbon dioxide ice, carbon monoxide ice, methane ice, all the frozen volatiles that form in the cold outer regions of planetary systems, gas vents into space, carrying dust particles with it. The dust scatters sunlight, forming the diffuse halo called a coma that can swell to sizes larger than Jupiter. If the comet is active enough, solar radiation pressure and the solar wind push gas and dust into a tail that streams millions of kilometers downwind, always pointing away from the sun, sometimes visible from Earth as a bright streak across the night sky. Brightening is predictable. Brightness correlates with proximity to heat. It is one of the oldest, most reliable patterns in solar system observation, documented in Chinese records from thousands of years ago, refined by European astronomers in the 17th century, modeled with increasing precision as spectroscopy and photometry advanced. Even comets that have grown dormant after many passes near the sun often show some residual activity, a faint puff of gas, a subtle brightening, something. 3I Atlas does not brighten. The object remains stubbornly faint, a point source barely distinguishable from the background stars, reflecting sunlight but emitting nothing detectable. No coma expands around it, no tail trails behind, no jets erupt from the surface. Spectrographic analysis struggles to extract meaningful data from such dim light. The signal-to-noise ratio hovers near the threshold where measurement becomes guesswork. But what little signal emerges suggests a surface coated in dark, carbon-rich material. Reflectivity hovers near 4%, comparable to charcoal or fresh asphalt, blacker than coal, quieter than stone. Observers increase exposure times. Larger telescopes are requisitioned. Requests are filed for time on instruments usually reserved for distant galaxies and exoplanet transits. Days pass, then weeks. The object drifts closer to perihelion, its closest approach to the Sun, still farther out than Mars ever ventures in its own elliptical orbit, roughly 1.8 astronomical units from the Sun's surface, and still, nothing changes. No outburst, no jet activity detected in any wavelength, no sudden surge of brightness that would indicate awakening ice responding to solar heat. It is not behaving like a comet, but its trajectory, its origin, its speed, its likely composition based on formation models of icy bodies in the outer regions of planetary systems all suggest it should be. The contradiction settles into the data like sediment at the bottom of a deep lake, unresolved, patient, accumulating slowly under the weight of each new observation that confirms the absence of what should be there. Scientists propose explanations. Perhaps the surface has been altered by cosmic rays during its long journey through interstellar space. Perhaps all the volatiles have already been lost in some previous encounter with a star, and what remains is just a desiccated core. Perhaps the volatiles are still there but buried beneath an insulating crust, too thick for solar heat to penetrate during this brief passage. Perhaps. 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 The mystery deepens with every non-detection. Somewhere in the cold, far beyond where planets cast shadows, far beyond where sunlight feels warm on any surface, the object that refuses to behave continues inward, silent and dim, carrying within its frozen or desiccated or altered frame a mystery that will outlast every attempt to solve it. At least for now, at least during this single crossing through the inner system that represents the only chance humanity will ever have to observe it directly. Only took 4.6 billion years to arrive. Only passing through for a few months. Only visible for a handful of weeks before it fades beyond the reach of even the largest telescopes. The universe is patient with its secrets. The catalogue of interstellar objects begins, as most astronomical catalogues do, with absence. For centuries, astronomers assumed that space between stars was empty of large bodies, or if not empty, then so sparsely populated that encounters with the solar system would be vanishingly rare, perhaps once per million years, perhaps never in the span of human observation. The mathematics suggested this. The galaxy is vast. The spaces between stars are vaster still. Objects ejected from distant planetary systems would disperse into the dark, diluted across cubic light-years of nothing, their odds of passing through any particular solar system approaching zero. Then one ʻOumuamua arrived in 2017, tumbling through the inner solar system at a sharp angle to the ecliptic plane, moving faster than anything bound to the sun should move. Its discovery was accidental, a consequence of improved survey technology rather than targeted searching. Pan-stars. The same telescope network that would later detect 3I Atlas caught the object as it was already leaving, already past perihelion, already accelerating back toward interstellar space. Observers had only weeks to gather data before it faded beyond detection. The scramble to understand ʻOumuamua revealed how unprepared the scientific community was for interstellar visitors. Telescopes were redirected mid-observation. Spectroscopic campaigns were hastily organized. Every available instrument capable of detecting such a faint, fast-moving target was pointed in the same direction. The data that emerged was fragmentary, contradictory, tantalizing. The object appeared elongated, perhaps cigar-shaped, perhaps pancake-flat light curves suggested unusual rotation and geometry. But the signal was noisy, the interpretations uncertain. It exhibited a small, unexplained acceleration as it departed the solar system, not the steady acceleration of a rocket or the predictable push of solar radiation pressure on a known surface, but something subtle, something that didn't quite match the models. Outgassing was the simplest explanation. Comets often accelerate slightly as ice sublimates and jets push against the surface, but no coma was detected, no tail, no spectroscopic signature of gas. The acceleration remained, documented in precise astrometric measurements, unaccompanied by any visible cause. Theories proliferated. Some researchers suggested it was a comet with unusual composition, perhaps nitrogen ice that would sublime without producing a detectable coma. Others proposed it was a fragment of a shattered planet, ejected during a catastrophic collision in another star system billions of years ago. A few speculated about artificial origin, though most astronomers dismiss this as premature given the limited data. The object became famous, discussed in news articles and academic papers alike, a mystery wrapped in insufficient observations. Then it was gone, receding into the dark, unreachable, its nature unresolved. 2 years later, Borisov arrived and behaved exactly as a comet should. Discovered by amateur astronomer Gennady Borisov using a homemade telescope in Crimea, the object displayed a bright coma visible even in modest instruments. Spectroscopy revealed the signatures of cyanogen and diatomic carbon, molecules commonly seen in solar system comets. The tail grew as the comet approached the Sun, streaming behind it in a familiar arc. Brightness increased on schedule. Observations accumulated. Models matched predictions. It was, in every measurable way, a normal comet except for its hyperbolic orbit, except for the fact that it came from interstellar space, except for the implication that such objects might be common after all. Borisov was cooperative. It allowed astronomers to refine their techniques, to practice observing interstellar visitors with adequate time and preparation. It confirmed that at least some objects wandering between stars are icy bodies, comet-like, presumably ejected from the outer regions of distant planetary systems during the chaotic early phases of planet formation when gravitational interactions scatter debris in all directions. Statistical models were updated. If 2 interstellar objects could be detected within 2 years, the population passing through the inner solar system at any given time might be substantial dozens, perhaps hundreds, most too faint or too far from Earth's orbital plane to be noticed. The galaxy, it seemed, was full of wanderers. Rogue planets ejected from their birth systems. Comets kicked into interstellar trajectories by close encounters with giant planets. Fragments from collisions, from tidal disruptions, from the violent processes that shape and reshape planetary systems over millions of years. Each star system, over its lifetime, likely ejects more mass than it retains. The leftovers of planet formation do not all settle into stable orbits. Gravitational scattering is efficient. Most of the solid material that forms in the outer regions of a young planetary system ends up elsewhere, ejected into interstellar space, or flung inward to collide with the star, or ground down into dust by collisions. The objects that remain in stable orbits are the survivors, the lucky ones, the minority. The space between stars is not empty. It is a slow sea of exiles. 3i Atlas joins this catalogue reluctantly. It fits the profile hyperbolic orbit, interstellar origin, likely composed of materials similar to comets or asteroids, but it refuses to confirm its nature through the usual means. It will not brighten, it will not outgas. It offers no spectroscopic clues, no coma, no tail. Nothing but a dim reflection of sunlight from a surface that absorbs most of the light that strikes it. Astronomers file it under interstellar object with a note, anomalous behavior. Non-cometary activity, despite likely volatile composition, origin and nature uncertain. The catalogue grows by one. The mysteries grow by several. Other objects have shown similar stubbornness. Within the solar system's own population of comets and asteroids, there exists a category called dark comets, objects that move like comets, showing non-gravitational accelerations consistent with outgassing, but produce no visible coma or tail. These objects are not common, but they are not unique either. Dozens have been tentatively identified, their accelerations too large to be explained by radiation pressure alone, too subtle to produce detectable gas emissions with current instruments. Perhaps 3I Atlas belongs to this category. Perhaps dark comets are more common in interstellar space than active ones, their surfaces altered by the long exposure to cosmic rays and interstellar radiation, their volatiles locked beneath crusts hardened over millions of years of slow chemistry. Perhaps what astronomers consider normal comet behavior is actually the exception, visible only when objects are young and unweathered, and most of the galaxy's wanderers are silent, dark, invisible, except when they pass close enough to a star to reflect a faint glimmer of light. The catalogue does not judge. It records. Object 3I Atlas detected January 2025 hyperbolic orbit, eccentricity approximately 1.2, perihelion 1.8 astronomical units, albedo approximately 4%, no detectable coma, origin unknown, nature uncertain, status ongoing. The list of things that refuse to orbit grows longer. The list of explanations grows longer too, but none of them feel complete. None of them settle the question. Somewhere in the equations, in the observations, in the careful measurements of position and brightness and spectrum, there is an answer. But the object does not offer it freely. It simply continues. A dark point against darker space, moving according to laws it has followed for millions of years, indifferent to names, to catalogues, to the brief attention of a species that has only just learned to look beyond its own star's immediate family, only took until the 21st century to notice. Only 3 confirmed detections so far. Only a matter of time before the next one arrives, carrying its own refusal, its own quiet contradictions, its own reminder that the universe is under no obligation to behave as expected. A comet, in the traditional understanding, is a simple machine, ice and dust, mixed together in proportions that vary but follow predictable patterns. Frozen volatiles, water, carbon dioxide, carbon monoxide, methane, ammonia locked into a matrix of silicate grains and organic compounds, all compressed into a body that ranges from a few hundred meters to tens of kilometers across. When distant from the sun, cold and inert, a comet is indistinguishable from an asteroid to the casual observer, just a dark, irregular lump drifting through space. But bring it closer to warmth, closer to the sun's radiation, and the machine activates. Sunlight strikes the surface. The dark material absorbs energy. Temperature rises. Though rises is a relative term from perhaps 50 Kelvin in the outer solar system to a few hundred Kelvin near Earth's orbit, still far below the freezing point of water by human standards, but warm enough for ice to sublimate in the vacuum of space. No liquid phase. Solid becomes gas directly, molecules breaking free from the crystalline lattice, lifting off into the near vacuum that surrounds the comet's nucleus. This is the beginning of activity. Gas vents from the surface, carrying with it fine dust particles that were embedded in the ice. The gas expands rapidly, forming a tenuous atmosphere around the nucleus, the coma. At first, the coma is small, barely larger than the nucleus itself, but as the comet continues inward, as solar heating intensifies, the coma grows. It can swell to hundreds of thousands of kilometers in diameter, larger than Jupiter, though still far more diffuse than any planetary atmosphere. The density is negligible, closer to a laboratory vacuum than to breathable air, but it is enough to scatter sunlight, enough to make the comet visible from Earth as more than just a point of light. The coma is neutral, uncharged, composed mostly of water vapor and dust. But solar ultraviolet radiation quickly begins to break apart water molecules, ionizing them, creating a population of charged particles that respond to the magnetic fields embedded in the solar wind. These ions are swept backward, away from the Sun, forming the characteristic ion tail, narrow, straight, often bluish in color, due to emission from carbon monoxide ions fluorescing under solar radiation. The dust, meanwhile, follows a different path. Dust particles are pushed by solar radiation pressure, the momentum of photons striking their surfaces and imparting a tiny but continuous force. Unlike the gas, dust does not accelerate rapidly away from the comet. It drifts, following curved trajectories that lag behind the comet's motion, forming the dust tail broad, diffuse, yellowish, because it simply reflects sunlight rather than emitting its own light. The dust tail can stretch for millions of kilometers, sometimes tens of millions. A gossamer streamer laid across the inner solar system like a banner announcing the comet's passage. All of this is predictable. Brightness follows a power law relationship with solar distance typically. A comet brightens by a factor of 4 for every halving of its distance from the Sun, though the exact exponent varies depending on the comet's composition and activity level. Observers can predict, months in advance, how bright a known comet will become at perihelion, how large its coma will grow, when it will be visible to amateur telescopes or even naked eyes. Some comets are more active than others. Fresh comets, making their first journey into the inner solar system from the Oort. Cloud that distant sphere of icy bodies stretching halfway to the nearest star tend to be more volatile rich, more prone to violent outbursts as pristine ice encounters solar heat for the first time. These are the comets that occasionally become spectacular. Great comets visible in daylight, tails spanning half the sky, objects remembered for generations. Other comets are quieter, Jupiter family comets, objects with shorter orbital periods that loop between Jupiter's orbit and the inner system every few years, have been heated many times. Their surfaces become depleted of the most volatile ices. Crusts form, insulating layers of dust and refractory material left behind as ice sublimates from below. These comets still activate, still produce comas and tails, but their brightness is more subdued, their outbursts less dramatic. They age, in a sense, becoming quieter with each passage near the Sun. But even the quietest solar system comets show some activity. Even the most depleted, most crusted, most aged objects produce at least a faint coma when they approach perihelion. Water ice is abundant in the outer solar system. Carbon dioxide ice sublimates at even greater distances, often producing pre-perihelion activity when the comet is still beyond Mars's orbit. The physics is robust, the observations span centuries, the pattern is consistent. This is what comets do. This is what they have always done, for as long as humans have watched the skies and recorded the movement of wandering lights against the fixed stars. This is the expectation, the baseline, the norm against which all behavior is measured. Except when it isn't. There are objects that defy easy classification. In recent years, as survey telescopes have become more sensitive and observational campaigns more thorough, astronomers have identified bodies that seem to occupy the boundary between asteroid and comet. Some asteroids, when observed carefully over months or years, reveal faint, transient comas that appear and disappear without obvious correlation to solar distance. Main belt comets. They are called objects orbiting in the asteroid belt that nonetheless show cometary activity, possibly due to ice deposits buried beneath their surfaces, exposed only when impacts or landslides remove overlying material. Other objects show non-gravitational accelerations without any visible outgassing. They deviate from purely gravitational trajectories, pushed by some force that is not sunlight pressure alone, yet they produce no coma, no tail, no spectroscopic signature of gas or dust. Dark comets, as some researchers have begun calling them, objects that are shedding mass, but invisibly, or in quantities too small to detect with current instruments. The solar system's inventory is messier than the neat categories suggest. Asteroids and comets grade into each other. Distinctions blur. Every careful survey reveals more exceptions, more objects that refuse to fit cleanly into the boxes prepared for them. But 3i Atlas is not a marginal case, not a borderline object showing faint, ambiguous activity. It shows none. Zero detectable coma. Zero spectroscopic evidence of gas emission. Zero dust production. Zero brightening as it approaches the sun. It is, by every measure, inert, dead, silent. And yet, its trajectory, its origin, its likely composition based on formation models, all suggest it should be icy, should be active, should behave like 2i Borisov behaved, like solar system comets behave, like the physics of sublimating ice in vacuum has always behaved for billions of years across the entire observed galaxy. It refuses. The refusal is not dramatic. There is no sudden shutdown, no visible transition from activity to silence. The object simply arrives already silent, already dark, offering no explanation, no cue to its history, no visible mechanism for its stubbornness. It is a comet that will not act like a comet, a visitor that will not announce itself, a data point that sits outside every trend line, patiently contradicting the accumulated wisdom of centuries. Scientists consult the literature. They review case studies of dormant comets, of asteroid-comet transition objects, of all the strange edge cases documented in decades of solar system observation. None of them quite match. None of them are as thoroughly unresponsive as 3i Atlas appears to be. The object does not care about precedent. It follows its trajectory, reflects its 4% of incident sunlight, and offers nothing more. The mystery is not in what it does, but in what it refuses to do. And refusal is harder to study than action. Absence provides no signal to analyze, no spectrum to decode, only a widening gap between expectation and observation. Only took 4 billion years of comet observations to find one this quiet. Only took traveling across light years of interstellar space to arrive at a solar system equipped to notice. Only passing through once, with no return visit scheduled. No second chance to check if the instruments were wrong, if the models were incomplete, if maybe next time it will behave. The observations accumulate slowly, carefully, with the methodical patience that characterizes professional astronomy. Each telescope contributes a few hours of data when the object crosses its field of view, when the moon is not too bright, when atmospheric conditions permit, when scheduling algorithms allocate time to this particular target among thousands of competing requests. The data streams into archives, distributed across servers on multiple continents, processed by software that flags outliers and measures brightness to a fraction of a percent. 3i Atlas remains a point source. In imaging, a point source means the object is too small to resolve. Its light concentrated into a single pixel or a tight cluster of pixels limited by the telescope's optical resolution and atmospheric turbulence. Stars are point sources. Distant galaxies, spanning hundreds of thousands of light years, appear as point sources if they are far enough away. A comet nucleus, typically a few kilometers across at most, is always a point source, but an active comet is not. The coma spreads the light across many pixels. The tail, if present, extends asymmetrically, creating an elongated brightness profile that is immediately distinguishable from stars. 3i Atlas shows no extension, no asymmetry, no fuzz, frame after frame, night after night. Different telescopes on different continents, different instruments with different optical characteristics, all record the same thing: a dim point of light that moves against the background stars at the predicted rate, following the calculated trajectory with precision that confirms it is real. It is there. It is where the ephemerides say it should be, but nothing more. Photometry provides brightness measurements across multiple wavelengths. Observers use standard filter systems: ultraviolet, blue, visible, red, infrared, building up a spectral energy distribution that reveals how the object reflects or emits light at different frequencies. The result is flat, unremarkable. The spectrum matches that of a dark, carbon-rich surface with no emission lines, no features that would indicate gas fluorescing under solar ultraviolet, no excess in the infrared that would suggest warm dust. Reflectivity stays constant near 4% across most wavelengths. This is unusually low. Most asteroids reflect 10 to 30% of incident sunlight. Even relatively dark carbonaceous asteroids typically manage 6 to 8%. 3I Atlas is darker than most of the objects in the solar system's inventory, darker than cometary nuclei that have been observed up close by spacecraft. Their surfaces revealed as mottled landscapes of dust and ice with albedos ranging from 5 to 15%. 4% is the reflectivity of charcoal, of soot, of material that has been processed, altered, cooked by radiation or heat until it absorbs nearly all the light that touches it. Spectroscopy, when conditions allow, reveals absorption features consistent with organic compounds, the broad, shallow bands characteristic of carbonaceous material, similar to what is seen in primitive asteroids and in the organic rich dust particles collected from Comet Wild 2 by the Stardust mission. But the signal is weak. The object is faint. Each spectrum requires hours of integration time on large telescopes, and even then the data is noisy, barely above the detection threshold. Claims about composition remain tentative. No emission lines appear in any spectrum. Water vapor, if present, produces characteristic absorption and emission features in the near-infrared. Cyanogen and diatomic carbon fluoresce in the blue and violet when excited by solar ultraviolet. Carbon dioxide ice has a distinctive signature in the infrared. None of these signatures are detected. Upper limits are calculated if water vapor is present in the coma. It is producing fewer than a certain number of molecules per second. The limits are tight. If gas is venting from the surface, the rate is at least 100 times lower than what 2I Borisov produced at a similar solar distance. Possibly 1,000 times lower, possibly absent entirely. Searches for dust are equally unproductive. Sensitive cameras image the region around 3I Atlas, looking for the faint, scattered light that would indicate dust particles in the vicinity of the nucleus. Stacking multiple images to increase sensitivity, filtering out background stars and cosmic rays, stretching the contrast to reveal faint features, standard techniques honed on decades of comet observations. The images reveal nothing: no coma, no jets, no arc-like structures that would indicate recent dust emission now drifting away from the nucleus. If dust is present, it is too sparse to detect. Calculations suggest that at the object's current brightness and distance, a dust coma with a diameter of even a few thousand kilometers should be visible with the instruments being used. The absence of any detection implies either no dust is being produced, or the dust production rate is so low that the resulting coma is smaller than the seeing disk, the blurring imposed by Earth's atmosphere, typically around 1 arc-second, which at the distance of 3I Atlas corresponds to roughly 1,000 kilometers. A coma smaller than 1,000 kilometers, for a nucleus perhaps a few kilometers across, would be negligible, invisible, indistinguishable from no coma at all. Astrometry tracks the object's position over time, measuring coordinates to milliarc-second precision by comparing the object's location to reference stars whose positions are known from previous surveys. Orbital calculations are refined with each new measurement. The trajectory becomes more certain. Predictions extend further into the future and backward into the past. The orbit is hyperbolic. No ambiguity remains. Eccentricity settles at 1.19, with an uncertainty of less than 1%. The object approached the solar system from the direction of the constellation Lynx, moving at roughly 33.2 kilometers per second relative to the Sun's rest frame. It will depart toward the constellation Telescopium, moving only slightly faster due to the Sun's gravitational assist, roughly 34 kilometers per second. Backtracking the trajectory suggests the object has been traveling through interstellar space for at least several million years, possibly much longer. Its velocity relative to the local standard of rest, the average motion of stars in the solar neighborhood is modest, around 15 kilometers per second. This implies it was not ejected violently from its home system, not flung out at high speed by a close encounter with a massive planet. Instead, it likely drifted out gradually, perturbed into a marginally unbound orbit by cumulative gravitational interactions, then released into the galaxy's slow tidal currents. Where it came from remains unknown. Tracing the orbit backward through the galaxy requires knowing the positions and velocities of nearby stars millions of years ago, accounting for their motions, the gravitational influence of the Milky Way's spiral arms, the perturbations from molecular clouds and other structures. The uncertainties compound quickly. Within a few million years, the uncertainty volume grows to encompass hundreds of cubic light-years. Within 10 million years, it spans a significant fraction of the local galactic neighborhood. No specific star system can be identified as the origin. The object could have been ejected from any of several thousand nearby stars, or from a system that has since moved far away, or from a system that no longer exists. Its host star long since evolved off the main sequence and dispersed its planets into the interstellar medium. It is anonymous. A traveler without a known home, without a documented history, arriving out of the dark with no story to tell except the story written in its motion and its stubborn silence. No brightening has been observed through perihelion. The object reached its closest approach to the Sun on March 7th, 2025, at a distance of 1.8 astronomical units, roughly 270 million kilometers, well inside Mars's orbit, but outside Earth's, positioned such that it was visible from Earth throughout its passage, but never particularly well placed, always requiring large telescopes, always faint. At perihelion, brightness should have peaked. Solar heating should have been at maximum. If volatiles were present anywhere on or near the surface, this was the moment they should have responded. This was the opportunity for the object to reveal itself, to confirm or deny its cometary nature, to offer some clue to its composition and history. It remained a point source. Magnitude 23, unchanged within measurement error, dark, inert, uncooperative. Observers filed their reports. Null result, no coma detected. No spectroscopic evidence of activity. The object does not behave like a comet. The object behaves like a very dark asteroid. But asteroids do not typically arrive on hyperbolic orbits from interstellar space, and the formation environment that produces dark asteroids does not easily eject them into the galaxy. The contradiction sits in the data, unresolved, a small discrepancy that might mean nothing or might mean everything, depending on what further observations reveal, if further observations are possible before the object fades beyond reach. Only took 54 days to pass perihelion, only one chance to observe it at maximum heating, Only a few more weeks of fading visibility before it becomes too dim for any telescope currently operating to track. The first interstellar comet that wasn't a problem arrived in August 2019, bright enough to be discovered by an amateur astronomer working from a personal observatory in Crimea. Gennady Borisov. Using a telescope, he built himself a 65-centimeter reflector assembled with patience and modest funding, was conducting a routine survey of the night sky when he noticed a faint smudge that moved between frames. He measured its position, submitted preliminary coordinates to the Minor Planet Center, and within days the global astronomical community had confirmed what the motion implied. Another visitor, another hyperbolic orbit, another object from interstellar space. But unlike ʻOumuamua, which had been discovered on its way out, already past perihelion, already fading, 2I Borisov arrived with time to spare. It was detected 3 months before perihelion, far enough out that observing campaigns could be organized, telescope time allocated, instruments calibrated. The object was approaching from the north, moving toward the inner solar system at a comfortable angle that would keep it visible from Earth for months. And it behaved beautifully. Within weeks of discovery, a coma became visible. Spectroscopy revealed emission lines from cyanogen CN, a molecule commonly found in solar system comets, produced when solar ultraviolet radiation breaks apart more complex organic compounds. Diatomic carbon appeared as well, another familiar signature. The spectral features match those of comets from the Oort cloud, pristine objects making their first passage through the inner solar system, their ices still unprocessed by previous solar heating. As 2I Borisov continued inward, brightness increased exactly as models predicted. The coma expanded, growing from a few thousand kilometers in diameter to more than 100,000. Observers tracked the development of the dust tail, measuring its length and curvature, calculating dust production rates from the scattered light. Everything fit. Every observation confirmed that this was, in all measurable respects, a normal comet, just one that happened to originate outside the solar system. Color measurements revealed a slightly red tint, suggesting the presence of organic compounds similar to those found in Kuiper Belt objects and long-period comets. Polarimetry indicated dust grain properties consistent with cometary dust, fluffy aggregates of silicates and carbonaceous material. Radio observations detected the hydroxyl radical OH produced by the photodissociation of water vapor, providing a direct measurement of water production rates. At perihelion, 2I Borisov was outgassing water at roughly 26 kilograms per second, along with comparable amounts of carbon monoxide and other volatiles. It was cooperative. It allowed itself to be studied. Every technique developed for observing solar system comets worked on 2I Borisov without modification. The data accumulated smoothly, published in dozens of papers over the following months, providing the first detailed look at a comet formed around another star. The findings were simultaneously exciting and reassuring. Exciting because they confirmed that other planetary systems produce objects similar to solar system comets, that the icy bodies wandering between stars are not exotic, not fundamentally different in composition or behavior. Reassuring because the physics worked, the models held, the expectations were met. Comets from interstellar space behave like comets. The universe is consistent. 2I Borisov set a standard. It provided a template, a baseline against which future interstellar visitors could be compared. When the next object arrived, astronomers would know what to expect. They would look for the coma, measure the outgassing rates, analyze the spectral signatures, compare the results to Borisov's well-documented activity. The procedures were established. The uncertainties were mapped. Then 3I Atlas arrived and refused the template entirely. No coma, no outgassing, no spectral features, no dust tail, no brightening curve. Nothing that 2I Borisov had done so cooperatively, so predictably, so thoroughly, just a dark, silent point moving through space at 33 kilometers per second, following a hyperbolic trajectory that confirmed its interstellar origin, but offering no other confirmation of anything. The contrast is stark. Placed side by side in the observational record, 2I Borisov and 3I Atlas appear to be entirely different classes of objects. One is unambiguously a comet icy, active, producing gas and dust exactly as expected. The other is unambiguously not active, producing nothing detectable, behaving more like a dark asteroid despite the implausibility of such an object arriving from interstellar space. Yet both traveled here from beyond the solar system. Both were ejected from planetary systems, presumably during the chaotic early phases of planet formation when gravitational scattering is most efficient. Both drifted through the galaxy for millions of years before intersecting the solar system's path through space. Both should, in principle, have similar compositions, icy bodies formed in the cold outer regions of their respective birth systems, beyond the snowline where water ice can condense, in the same temperature and pressure regimes that produce the Kuiper Belt and Oort cloud. Why does one behave like a textbook comet and the other remain silent? The question does not have an obvious answer. Researchers propose several possibilities, none entirely satisfying. Perhaps 3I Atlas is significantly older than 2I Borisov, has spent longer in interstellar space, has been subjected to more intense weathering by cosmic rays and interstellar radiation. Cosmic rays' high-energy protons and atomic nuclei accelerated to near-light speeds by supernova shocks and other violent events constantly bombard objects in interstellar space. They penetrate surfaces, break chemical bonds, alter crystal structures, and over millions of years can transform the outer layers of icy bodies into a radiation-processed mantle. This mantle, sometimes called an irradiation crust, could act as insulation, preventing heat from penetrating to the volatile-rich layers below. Even when the object approaches the sun, even when its surface warms to temperatures where ice should sublimate, the crust might remain intact, sealing the volatiles beneath an impermeable layer of refractory organic compounds and amorphous carbon. But cosmic ray weathering affects all objects in interstellar space. 2I Borisov should have experienced similar processing, yet it activated without difficulty. The difference in exposure time would need to be substantial, perhaps millions of years, versus tens of millions of years, and even then. The effect would depend on the original composition, the porosity of the material, the thickness of the surface layers. Another possibility, perhaps. 3I Atlas was already depleted of volatiles before it entered interstellar space. Perhaps it experienced multiple close encounters with its host star during the ejection process, heating up repeatedly, venting its most volatile ices, leaving only refractory material behind. Perhaps it was ejected from the inner regions of its birth system rather than the outer regions, a rocky core rather than an icy body, misidentified as a comet based solely on its interstellar origin. But rocky objects are harder to eject. They form closer to the star, in regions where planetary masses are larger and gravitational scattering is more likely to result in inward migration or collisions rather than ejection. The efficiency of ejecting rocky material into interstellar space is much lower than the efficiency of ejecting icy material. Statistically, most interstellar wanderers should be comet-like, not asteroid-like. Perhaps 3I Atlas represents a rare exception, an outlier, a statistical fluctuation. Perhaps for every object like 2I Borisov, There are 10 or 100 silent ones, like 3I Atlas, too dark to detect unless they pass very close to Earth. Their population underestimated because they are harder to find. The sample size is too small to judge. 3 confirmed interstellar objects, 2 of them cometary in origin, 1 active and 1 not. 3 data points cannot define a distribution. Every additional detection will shift the statistics, reshaping the understanding of what is typical and what is anomalous in the population of objects drifting between stars. For now, 2I Borisov stands as the well-behaved example, the one that matched expectations, the one that allowed itself to be understood. 3I Atlas stands as the refusal, the exception, the object that arrived like a stranger who forgot the script and will not explain why. Scientists continue to observe both trajectories figuratively, since 2I Borisov has long since faded from view, now well beyond Neptune's orbit, receding into the outer dark where it will travel for millions of years before approaching another star. 3I Atlas is still visible, barely. To the largest telescopes, tracked carefully as it crosses the inner solar system and begins its own long departure. Neither object will return. Neither can be revisited if new questions arise, if better instruments become available, if someone thinks of a measurement that should have been made but wasn't. Interstellar objects pass through once. The data collected during their brief visibility is the only data that will ever exist for those specific objects. Only took 6 years between first interstellar detection and third, only 2 behaved similarly. Only one taught astronomers to expect consistency, and only one reminded them that consistency is not guaranteed, that the universe is under no obligation to send cooperative examples, that sometimes the most interesting objects are the ones that refuse to perform as expected. Composition begins with light, not the light. The object emits. 3I Atlas emits nothing detectable but the light it reflects, the sunlight that strikes its surface and bounces back toward Earth, carrying within its spectrum the faint fingerprints of whatever molecules and minerals exist on that distant, dark surface. Spectroscopy is the art of reading those fingerprints, separating reflected light into its constituent wavelengths, searching for the absorption bands and emission lines that reveal chemical composition. The spectrum of 3I Atlas is frustratingly bland, flat across most wavelengths, featureless, dominated by the continuum, the smooth background of reflected sunlight without the sharp features that would indicate specific molecules absorbing at characteristic frequencies. What little structure exists suggests organic compounds, carbonaceous material, the same complex mixtures of carbon, hydrogen, oxygen, and nitrogen that coat many primitive asteroids and cometary nuclei. These organic compounds are not life, not biological, but the products of chemistry in cold environments where ultraviolet radiation and cosmic rays process simple molecules into more complex structures over millions of years. Methane becomes ethane. Ethane becomes longer carbon chains. Carbon chains cross-link into terry substances that resemble asphalt more than anything living. The result is a dark, carbon-rich surface that absorbs most incident light, reflecting only a small percentage diffusely in all directions. This material is common in the outer solar system. It coats the surfaces of Kuiper Belt objects, darkens the moons of the giant planets, fills the spaces between ice grains in cometary nuclei. It is expected. It is not surprising. What is surprising is the absence of ice signatures accompanying it. Water ice has a distinctive spectrum. In the near-infrared, around 3 micrometers wavelength, water ice produces strong absorption bands due to vibrational transitions in the OH bond. These bands are deep, easily detectable even when ice makes up only a small fraction of the surface. Spacecraft visiting comets have consistently found water ice exposed in patches on cometary nuclei, revealed by spectroscopy as bright regions contrasting with the darker organic-rich terrain. 3I Atlas shows no water ice signature. None in the near-infrared. None in the visible. None at any wavelength where observers have sufficient sensitivity to detect it. Either the surface contains no water ice, or the ice is buried beneath a layer of organics thick enough to mask its spectral signature completely. Carbon dioxide ice, which is more volatile than water ice and sublimates at greater distances from the sun, also shows no evidence of its presence. Nor does carbon monoxide, methane, ammonia, or any of the other ices commonly found in comets and icy outer solar system bodies. The spectrum is consistent with a surface composed almost entirely of refractory material substances that do not easily vaporize, that remain solid at the temperatures 3I Atlas experiences during its passage through the inner solar system. Two explanations present themselves. Either the object genuinely lacks volatiles, having lost them through some process before or during its journey through interstellar space, or the volatiles are still present but hidden beneath an insulating crust that prevents them from sublimating and also obscures their spectral signatures. The first explanation requires a mechanism for volatile depletion. Comets can lose their ice through repeated heating during multiple passes near the Sun, gradually sublimating away the surface layers until only refractory lag deposits remain. But 3I Atlas has never passed through a solar system before, or if it has, the event occurred so long ago that the object's trajectory has been completely randomized by galactic tidal forces, erasing any memory of its original orbit. Interstellar space itself can erode volatiles, but the process is slow. Cosmic rays penetrate only the outermost few meters of material. Sputtering by the interstellar medium, the thin gas between stars removes material atom by atom from exposed surfaces, but at a rate measured in nanometers per million years. An object a few kilometers across could drift through interstellar space for hundreds of millions of years and lose only a negligible fraction of its mass to sputtering. The second explanation, hidden volatiles beneath a crust, is more plausible but raises its own questions. How thick would the crust need to be? Calculations suggest that an insulating layer just a few centimeters thick could prevent solar heat from reaching buried ice during a brief passage through the inner solar system. The thermal diffusivity of organic-rich material is low. Heat conducts slowly through it. By the time warmth penetrates from the surface to depths where ice might reside, the object could already be receding, moving back into the cold where surface temperatures drop below the sublimation point. But a few centimeters is fragile. Micrometeorite impacts should erode such a thin crust over millions of years in interstellar space. Each impact vaporizes a small crater, exposing fresh material beneath. After sufficient time, the surface should be gardened, churned, a mixture of crust and underlying material rather than a uniform insulating layer. Perhaps the crust is thicker, perhaps meters thick, or tens of meters. Thick enough to survive micrometeorite gardening, thick enough to insulate effectively even against prolonged solar heating. But how does such a crust form in interstellar space, where temperatures hover just a few degrees above absolute zero? Chemistry proceeds slowly, if at all. Radiation processing can alter surface materials, cross-linking organic molecules into more complex structures. But building a meter-thick crust through radiation alone would require timescales approaching the age of the solar system. Perhaps the crust formed before ejection, while the object was still in its birth system. Perhaps it was heated during the scattering process, approached close to its host star, experienced a brief, intense period of sublimation that left behind a thick lag deposit. Perhaps that lag deposit then protected the interior through the long journey across light years, preserving whatever volatiles remained beneath. Speculation accumulates. Each explanation requires assumptions, requires particular conditions to be met, requires the object's history to have unfolded in a specific sequence. Without additional data, without direct measurements from a spacecraft encounter, without spectroscopic confirmation of what lies beneath the surface, all explanations remain plausible and none can be confirmed. What is known with certainty is limited. The surface is dark, carbonaceous, spectrally bland. What is absent is equally certain: no water ice signature, no emission from sublimating volatiles, no dust coma that would indicate material lifting from the surface. The object is, in its current state, inert. Whether it has always been inert, or whether the inertness is temporary, imposed by a crust that might crack or erode under different conditions, remains unknown. Comparisons to solar system objects are instructive but incomplete. Some asteroids have surfaces as dark as 3I Atlas, carbonaceous C-type asteroids, which dominate the outer main belt and are thought to be remnants of the early solar system's icy planetesimals, have albedos as low as 3 to 5%. These asteroids are believed to contain significant water ice beneath their surfaces, locked into hydrated minerals, but the ice is chemically bound, stable at room temperature, not prone to sublimation. Other asteroids have shown unexpected activity. In recent years, several main belt asteroids have been observed producing transient comas, brief episodes of dust emission that suggest the presence of buried ice or volatile-rich pockets exposed by impacts or thermal stresses. These objects, termed main belt comets, challenge the traditional distinction between asteroids and comets. They look like asteroids most of the time, inactive and inert, but occasionally they act like comets. 3I Atlas might belong to a similar category, an object that is mostly inert, mostly refractory, but that might, under the right conditions, reveal hidden volatiles. Perhaps if it had approached closer to the Sun, if perihelion had been at 1 astronomical unit instead of 1.8, the additional heating would have been enough to penetrate the crust, to trigger sublimation, to produce a detectable coma. Perhaps, but perihelion has passed. The object is now receding, moving back into the cold, and no outburst occurred. If volatiles exist beneath the surface, they will remain undetected, at least during this passage, at least until the object travels for millions of years and perhaps encounters another star, another moment of heating, another chance to reveal what it carries inside. The missing volatiles sit at the center of the mystery. Without them, 3I Atlas is simply a dark asteroid that happens to have an interstellar origin unusual, noteworthy, but not fundamentally puzzling. With them, buried and hidden, the object becomes a different kind of puzzle, a comet that refuses to act like one, a body that carries ice through interstellar space but will not release it, a visitor that keeps its composition secret even when bathed in sunlight. Only took millions of years to arrive. Only spent a few months warm enough to potentially activate. Only needed a slightly thinner crust, a slightly closer perihelion, a slightly different thermal history, and the mystery might never have existed at all. The galaxy is full of wanderers. This is not speculation, but consequence mathematical inevitability derived from the physics of planet formation and the efficiency of gravitational scattering. When a planetary system coalesces from a rotating disk of gas and dust around a young star, most of the solid material does not end up in planets. Most of it ends up elsewhere. Some falls into the star, spiraling inward through the disk, accreting onto the stellar surface, adding to the star's mass in quantities too small to significantly alter its evolution. Some remains in the disk as dust, ground down by collisions until the particles are fine enough to be blown away by stellar winds or radiation pressure. Some collects into asteroids and comets that survive in relatively stable orbits for billions of years. And some is ejected, flung outward by gravitational encounters with forming planets, accelerated to velocities exceeding the system's escape speed, sent tumbling into interstellar space to drift until encountering another star, or until the heat death of the universe, whichever comes first. The efficiency of this ejection process is high. Simulations of planetary system formation consistently show that for every mass unit retained in planets and stable debris, several mass units are ejected. Jupiter-sized planets are particularly effective at scattering material. Their gravitational influence extends far into the outer regions of their systems, perturbing smaller bodies, altering orbits, occasionally flinging objects onto hyperbolic trajectories with a single close encounter. The ejected material is predominantly icy. Rocky material forms in the inner regions of planetary systems, closer to the star where temperatures are high enough to prevent volatile ices from condensing. These regions are also where the largest planetary masses typically assemble, where gravitational interactions are most likely to result in collisions or inward migration rather than outward ejection. Ice forms farther out, beyond the snowline, in the cold outer regions where water vapor condenses into solid grains. These regions produce comets, icy planetesimals, the building blocks of giant planets' cores. When giant planets scatter this icy material, much of it escapes the system entirely. The result, over the lifetime of a typical planetary system, is the ejection of billions upon billions of cometary bodies into the interstellar medium. Each planetary system contributes its population of exiles. Multiply by the 200 billion stars in the Milky Way, many of them accompanied by planets, many of those planets capable of scattering material, and the cumulative population of interstellar objects becomes staggering. Estimates vary, but a conservative calculation suggests there are trillions of interstellar comets drifting through the galaxy at any given moment, possibly quadrillions. The uncertainty is large because the detection rate is still too low to constrain the population precisely. 3 confirmed detections in 8 years of intensive surveying implies a certain flux through the inner solar system, but converting that flux into a total galactic population requires assumptions about the velocity distribution, the size distribution, the trajectories. If the average interstellar object moves at 20 kilometers per second relative to the local standard of rest, typical for objects ejected by planetary scattering, then the space density can be estimated. At that density, the average distance between neighboring interstellar objects is measured in tens of billions of kilometers, vast by human standards, tiny by galactic standards. The interstellar medium is not empty of large bodies. It is sparsely populated, but populated nonetheless. Most of these objects are small, a few kilometers across or less, invisible at interstellar distances, detectable only when they pass through a planetary system and reflect sunlight or, if volatile rich, activate and produce a visible coma. Larger objects are rarer. Following a size distribution similar to what is observed in the Kuiper belt and asteroid belt, many small objects. Fewer large ones. The exact power law slope still uncertain. 3I Atlas, estimated to be between 1 and 5 kilometers in diameter based on its brightness and assumed albedo, falls within the typical size range for detectable interstellar objects. Not unusually large, not unusually small, just an average wanderer passing through. Where it came from, which specific planetary system ejected it, remains unknown and likely unknowable. Tracing trajectories backward through the galaxy is straightforward in principle, but complicated in practice by the uncertainties in stellar motions, by the gravitational perturbations from the Milky Way's spiral arms, and from molecular clouds encountered during the journey, by the accumulated effect of millions of small gravitational tugs from distant stars. Researchers have attempted to identify candidate origin systems by backtracking 3I Atlas's trajectory and looking for stars that were in close proximity within the past few million years. The search yields several candidates nearby stars whose past positions intersect with the object's probable path. Given the uncertainties in both the object's velocity and the star's motions, but nearby in this context means within a few hundred light years, and within the past few million years means uncertainties in timing that span hundreds of thousands of years. The volume of space-time to search is enormous. Dozens of stars fall within the plausible region. None stand out as particularly likely. None show characteristics that would make them especially efficient at ejecting comets, though. In truth, most stars are efficient at ejecting comets during the early phases of planetary system formation. So, the lack of distinguishing features is not informative. One candidate is a young star, only a few 100 million years old, still surrounded by a debris disk, a promising sign, since young systems with substantial debris are likely still in the process of scattering material, but the geometry does not quite work. The timing requires 3I Atlas to have been ejected at a very specific velocity, at a very specific angle, to arrive at the solar system when and how it did, possible, but requiring a level of fine-tuning that reduces the probability. Another candidate is an older star, several billion years old, more like the Sun. This star passed within a few light years of the Sun's current position roughly 3 million years ago, a close encounter by galactic standards, though not unusually close. If 3I Atlas was ejected from this system billions of years ago during its planet formation phase, it could have wandered through the galaxy for eons before the random walk of its trajectory brought it near the Sun at the same time that this particular star happened to be in the vicinity. But correlation is not causation. The number of stars that have passed within a few light years of the Sun's position over the past few million years is not small. The fact that one or more of them align approximately with 3I Atlas's arrival does not prove origin. It merely suggests possibility. Without more precise measurements of the object's velocity vector, without better knowledge of the gravitational perturbations it experienced during its journey, without a way to chemically fingerprint its composition and compare it to known planetary systems, the origin remains speculative. 3I Atlas is anonymous, a wanderer without a documented home. Its history written in motion and silence, but not in any language astronomers can fully read. The larger question is not where this specific object came from, but what it represents. Is it typical of interstellar comets, most of which are too faint or too inactive to detect? Is it an outlier, a rare example of an object that has been depleted or crusted or altered in ways that most interstellar wanderers avoid? The sample size of 3 ʻOumuamua Borisov. Atlas is too small to answer definitively. ʻOumuamua was strange, elongated, accelerating, producing no visible coma despite the non-gravitational force. Borisov was normal, icy, active, textbook behavior. Atlas is silent, dark, inert, refusing to outgas. 3 objects, 3 different behaviors. Either the diversity is real, reflecting a wide range of compositions and histories among interstellar wanderers, or the sample is biased, selecting for the unusual because the typical objects are too faint to detect. Future surveys will help. Larger telescopes with more sensitive detectors, Automated systems capable of scanning the entire sky every few nights, searching for moving objects, calculating orbits in real time. The Vera Rubin Observatory, scheduled to begin full operations soon, will detect faint moving objects at unprecedented rates. Estimates suggest it might find several interstellar objects per year once it reaches full survey speed. If those objects show similar diversity, some active, some inactive, some strange and inexplicable, then diversity is real, and the interstellar population is heterogeneous, reflecting different formation environments, different ejection mechanisms, different histories of weathering and alteration. If most of them behave like Borisov, then Borisov is typical, and ʻOumuamua and Atlas are outliers, interesting but not representative. The galaxy will answer eventually. It has already sent thousands of wanderers through the solar system during the time humanity has existed, most of them passing unnoticed in the dark. It will send thousands more in the coming centuries. Some will be bright enough, close enough, interesting enough to study in detail. Each will add to the inventory, reshaping the statistical distribution, clarifying what is common and what is rare. For now, 3i Atlas drifts outward, carrying with it the mystery of where it came from, what it is made of, why it refuses to behave as expected. It does not explain itself. It simply moves, following the trajectory carved by gravity, silent as stone, dark as the space between stars. Only took a few million years to cross the light years between systems. Only passing through this one briefly, visible for weeks, then gone. Only one more data point in a catalog that will grow, slowly, as the galaxy continues its patient work of sending wanderers past every star, every world, every observer patient enough to watch the sky and notice the things that do not belong. Dormancy is not death, but suspension, a state where volatiles remain but refuse to sublimate, where the machinery of cometary activity exists but does not engage, where the potential for outgassing persists beneath surfaces that have been rendered inert by time or temperature or the patient work of chemistry. Many comets in the solar system have entered dormancy after repeated passages near the Sun, their surfaces transformed by cycles of heating and cooling into mantles that seal away whatever ice remains below. The process is gradual. Each time a comet approaches perihelion, solar radiation warms the surface. Ice sublimates, venting gas that carries dust particles into space. But not all the dust escapes. Some falls back, settling onto the surface as the comet recedes and outgassing diminishes. Other dust never lifts off at all heavier grains, particles too large to be carried by the thin stream of sublimating gas, material too deeply embedded in the matrix to be freed. Over multiple orbits, a lag deposit accumulates, a layer of dust and refractory material left behind as the ice beneath it vaporizes and escapes, building up gradually like sediment at the bottom of a drying lake. This layer insulates. It blocks sunlight from penetrating to the ice below. It reduces the surface temperature through lower thermal conductivity. Eventually, if the layer grows thick enough, it can suppress sublimation entirely, even when the comet passes through perihelion, even when the surface is bathed in direct sunlight. The comet becomes dormant. It stops producing a coma, stops developing a tail, stops brightening in the expected way. To an observer, it looks like an asteroid, dark, inactive, unremarkable. Only its orbit reveals its cometary origin. If the orbit is sufficiently eccentric or inclined to distinguish it from the asteroid population. Several dormant comets have been identified in the solar system, usually by comparing their orbital elements to those of known cometary families, or by detecting faint, sporadic activity that suggests buried ice occasionally breaking through the crust. These objects are classified as dormant or extinct comets, transition objects between the active comet population and the asteroid population. Reminders that the distinction between categories is not always sharp, but dormancy in the solar system requires multiple heating cycles. It requires the comet to approach the sun repeatedly, to sublimate ice repeatedly, to build up the insulating lag deposit layer by layer over thousands or tens of thousands of years. A comet making its first passage into the inner solar system, arriving fresh from the Oort cloud, does not have a lag deposit. It activates readily. It behaves like 2I Borisov behaved: bright, active, cooperative. 3I Atlas has never been heated before. Or rather, it has never been heated by the sun before. Its trajectory is hyperbolic, unbound, arriving from interstellar space where it has drifted through the cold dark for millions of years without encountering any star closely enough to experience significant solar radiation. If it originated in another planetary system, as its velocity and trajectory strongly suggest, then it was ejected early, during or shortly after the formation of that system, before it had the opportunity to make multiple passages near its host star. So dormancy, in the conventional sense, does not explain 3I Atlas's inactivity. The object should not have a lag deposit built up from repeated heating. It should be pristine, or at least as pristine as an object can be after millions of years in interstellar space, unless the surface was altered before ejection, unless the object experienced heating in its birth system, perhaps a close approach to the star during the scattering event that ultimately ejected it, perhaps a period of residence in the inner regions of the system before being perturbed outward. Such heating could have produced a lag deposit, could have depleted the surface layers of volatiles, could have left the object crusted before it ever entered interstellar space. But this scenario requires specific conditions. Most scattering events involve interactions with giant planets in the outer regions of planetary systems, far from the star, where temperatures are too low to cause significant sublimation. Objects are typically ejected from the cold outer regions, not the warm inner regions. Heating during ejection is possible, but not common. Another possibility, the dormancy is not due to a lag deposit, but to a different kind of surface alteration, one that occurs in interstellar space itself. Cosmic rays, stellar winds, the diffuse ultraviolet radiation from distant stars. These processes can modify surfaces over millions of years, breaking chemical bonds, creating new compounds, polymerizing organic molecules into complex structures that resist sublimation. This irradiation crust, as it is sometimes called, forms slowly but inexorably. Cosmic rays penetrate the outer few meters of material, depositing energy, ionizing molecules, initiating chemical reactions that would not occur in the absence of radiation. Water ice can be converted into hydrogen peroxide and molecular oxygen. Simple organics can cross-link into tarry residues. The crystalline structure of ice can be damaged, amorphized, made less prone to sublimation by disrupting the ordered lattice that allows molecules to escape cleanly from the surface. Laboratory experiments have simulated these processes, bombarding ice samples with high-energy protons and measuring the resulting changes in composition and sublimation rate. The results show that irradiated ice can become significantly less volatile than pristine ice, requiring higher temperatures to sublimate at the same rate. A few million years of cosmic ray exposure could, in principle, produce a surface layer resistant enough to sublimation that even solar heating at 1.8 astronomical units is insufficient to trigger detectable activity. But the experiments also show that irradiation effects are limited in depth. Cosmic rays, despite their high energy, do not penetrate deeply. A few meters at most, often less, depending on the particle energy and the material density. Below the irradiated crust, the ice should remain pristine, unaltered, ready to sublimate if exposed. And surfaces are not static. Micrometeorite impacts continuously churn the outer layers of objects in space, excavating small craters, exposing fresh material, mixing irradiated crust with underlying pristine ice. This gardening process, well documented on airless bodies in the solar system, should prevent a uniform irradiation crust from forming. The surface should be patchy, a mixture of altered and unaltered material, with at least some regions where pristine ice is accessible to solar heating. Yet 3I Atlas shows no patches of activity, no localized jets or outbursts that would indicate fresh ice exposed in limited areas. The inactivity appears global, uniform, as if the entire surface is sealed by a crust thick enough and complete enough to suppress all outgassing everywhere. This uniformity is puzzling. It suggests either an unusually thick crust, far thicker than cosmic ray penetration alone can produce, or an unusually low impact rate in interstellar space, insufficient to garden the surface and expose fresh material, or some other process not yet considered, some mechanism that produces global dormancy without requiring repeated solar heating. The mystery compounds. Every explanation requires special conditions, requires the object to have followed an unusual path, to have experienced an atypical history, and while any individual object might be unusual, might be an outlier, the growing sense among researchers is that 3I Atlas may not be unique, that there may be many such objects in the interstellar population, dark and dormant, passing through unnoticed because they do not activate, because they do not produce the bright comas and tails that make comets easy to detect. If true, if a significant fraction of interstellar comets are dormant, then the population estimates need revision. Detection surveys are biased toward active objects. Inactive objects are much harder to find fainter, lacking the extended coma that makes them stand out from background stars. The true flux of interstellar visitors might be much higher than current estimates suggest. Most of them silent, most of them dark, most of them passing through the solar system without attracting attention. 3I Atlas, in this interpretation, is not an anomaly, but a representative, a glimpse of the typical interstellar object that happens to have passed close enough and at the right angle to be detected despite its dormancy. The silent majority finally noticed. Or it is an outlier after all, unusual in its inactivity, and most interstellar objects behave like Borisov, active, cooperative, easily studied. The answer requires more data, more detections, a larger sample to distinguish between common and rare. For now, dormancy remains a hypothesis, plausible but unproven, offering an explanation for 3I Atlas's silence but raising as many questions as it answers. Why dormant? How dormant? Dormant since ejection or dormant only recently? Dormant throughout or dormant only on the surface, with active ice buried beneath, waiting for some future moment of exposure that will not come during this passage. That might never come. The object does not clarify. It drifts outward, inert, carrying its dormancy with it, offering no clue whether the silence is permanent or temporary, whether it has always been this way, or whether it once, long ago, in some other solar system, in some earlier era, glowed and vented gas like the comets humanity has studied for centuries. Only took millions of years in interstellar cold to potentially seal it. Only takes a few months near the sun to test whether the seal holds. Only get one test, one passage, one chance to observe whether dormancy can be broken or whether it persists unchanged through heat and light and the brief attention of curious observers. The dark comet hypothesis emerges not from Three-Eye Atlas alone, but from a growing catalogue of objects that refuse to fit cleanly into established categories. Astronomers, who prefer clear taxonomies, who organize the solar system into planets and dwarf planets and asteroids and comets, find themselves confronted with bodies that occupy the spaces between definitions, that exhibit characteristics of multiple categories simultaneously, that move in ways that suggest one nature while appearing in ways that suggest another. The story begins with precise astrometry, the careful measurement of object positions over time, tracking their motion against the background stars with millisecond precision, fitting the observations to orbital models that account for gravitational forces from the Sun and planets. For most objects, these models work perfectly. The trajectory can be predicted years in advance. The object appears where calculations say it should appear, moving at the speed calculations predict, following the path carved by gravity alone. But some objects deviate, slightly, measurably, persistently. Their positions drift away from purely gravitational predictions by amounts too large to be measurement error, too systematic to be random. Something is pushing them, accelerating them in directions that cannot be explained by gravitational forces alone. For comets, the explanation is straightforward outgassing. When ice sublimates from a rotating nucleus, the escaping gas produces a jet, a directed thrust, a rocket effect that nudges the comet's trajectory. This non-gravitational acceleration has been observed and measured for centuries, first noticed by astronomers who realized that comets did not return to perihelion at exactly the predicted times. Their orbits perturbed slightly by the recoil from their own activity. The effect is predictable. The magnitude of the acceleration correlates with the comet's brightness, with the amount of gas being produced, with the distance from the Sun. Models account for it. Orbital predictions incorporate it. The physics is understood. What is not understood is why some objects show non-gravitational accelerations without showing any visible activity. The first such object to draw significant attention was ʻOumuamua. As it departed the solar system in late 2017, precise astrometric measurements revealed a small but definite acceleration, deviating from a purely gravitational trajectory by an amount that could not be ignored. The acceleration was consistent with outgassing, with a jet pushing the object along its spin axis, but no coma was detected. No spectroscopic signature of gas, no evidence that anything was leaving the surface. Researchers proposed alternative explanations, perhaps radiation pressure on an unusually reflective or oddly shaped object, perhaps hydrogen gas, which is difficult to detect spectroscopically, outgassing from water ice dissociated by cosmic rays, perhaps a nitrogen ice surface, sublimating without producing detectable emission. None of the explanations were entirely satisfying. Each required assumptions about the object's composition or shape that could not be independently verified. Then, similar objects began appearing in the solar system's own population. Surveys detected asteroids objects classified as asteroids based on their appearance, their lack of coma, their residence in asteroid-like orbits that nonetheless showed small non-gravitational accelerations. Not as large as typical cometary accelerations, but present, measurable, statistically significant. These objects were dubbed dark comets, a term that acknowledges the ambiguity, the refusal of nature to respect human categories. They look like asteroids. They move like comets. They are neither and both. By 2024, a few dozen dark comets had been tentatively identified in the solar system. Their accelerations, detected through careful analysis of years or decades of astrometric data. Most are small, a few hundred meters across, residing in the inner solar system or the main asteroid belt. Their accelerations are tiny, typically less than 1/1,000,000th of a meter per second, squared imperceptible over short time scales, but accumulating over years into measurable deviations from gravitational predictions. The accelerations suggest mass loss, something leaving the surface, but the rates must be very low. If gas is outgassing, it is doing so at levels 1,000 times or more below typical cometary rates, producing comas too tenuous to detect with current instruments, tails too faint to photograph. If the mass loss is not gas but something else, dust ejected by meteorite impacts, particles lifted by electrostatic forces, materials shed through rotational instability, then the mechanisms are unclear, the physics uncertain. 3I Atlas may belong to this category: astrometric measurements. As the object crosses the inner solar system, are being collected and analyzed, compared to purely gravitational models. The observations are challenging. The object is faint, the exposure times long, the number of reference stars in each field limited, but preliminary analysis suggests a possible non-gravitational component to the motion, a slight deviation consistent with a force of roughly the same magnitude as seen in some solar system dark comets. If confirmed, if the acceleration is real and not an artifact of measurement noise or systematic errors, then 3I Atlas is outgassing nature despite the lack of a visible coma, despite the absence of spectroscopic signatures, despite appearing completely inert to every observational test applied. Something is leaving the surface, something too faint or too diffuse or too transparent to detect, but real, exerting force, altering the trajectory by tiny increments that add up over weeks and months into measurable offsets. What could produce such invisible outgassing water vapor is detectable, should be detectable, has been detected in many comets at much greater distances from the Sun. Carbon dioxide produces strong infrared signatures. Organics, if vaporizing, should show spectral features. The usual suspects do not fit. Nitrogen is a possibility. Molecular nitrogen. N2 is relatively inert, does not fluoresce strongly under solar ultraviolet, produces no bright emission lines in the visible spectrum. If the surface is composed of nitrogen ice, a suggestion made for ʻOumuamua. Though controversial, then sublimating nitrogen could accelerate the object without producing a detectable coma. But nitrogen ice is volatile, more volatile than water, more volatile even than carbon monoxide. It should sublimate vigorously at the temperatures 3I Atlas experiences. It should produce measurable effects in the infrared, should be detectable through thermal emission if nothing else. Unless the nitrogen ice is buried, insulated beneath a crust that limits the sublimation rate, that allows just enough gas to escape to produce the observed acceleration, but not enough to create a visible coma. A fine-tuned scenario, requiring specific crust thickness, specific thermal properties, specific subsurface temperatures possible, but requiring many assumptions. Another possibility: the outgassing is not molecular but atomic, not driven by sublimation but by sputtering or some other surface process. Energetic particles from the solar wind strike the surface, knock atoms loose, send them flying into space at speeds too high to form a gravitational bound coma. The ejected atoms disperse rapidly, never accumulating into a detectable cloud around the nucleus, but still carrying momentum, still producing a net force on the object. But sputtering rates are low, typically insufficient to produce the observed accelerations unless the object is very small or the solar wind much more intense than usual. And sputtering does not vary strongly with solar distance, would produce a nearly constant acceleration rather than the distance-dependent effect expected if sublimation is the driver, or perhaps the mass loss is not gas at all, but dust, ejected by some mechanism other than gas drag. Rotational disruption: some objects spin fast enough that centrifugal forces overcome the weak gravity holding them together, flinging particles from the equator into space. Electrostatic levitation surfaces exposed to solar ultraviolet and the solar wind become charged, and fine dust grains can be lifted by electric fields. Thermal fracturing, repeated heating and cooling stresses the material, causing cracks to propagate, fragments to detach. Each mechanism has been observed or inferred in various solar system bodies. Each could, in principle, produce mass loss without a visible coma. If the particle sizes are large enough that they do not scatter light efficiently, if the ejection velocities are high enough that particles disperse quickly, if the rates are low enough that the density never becomes sufficient for detection, the dark comet hypothesis does not specify the mechanism. It simply acknowledges the observation some objects accelerate as if they are losing mass, but do not show the visible signs of that mass loss. The gap between motion and appearance is real, documented in multiple objects, reproducible in different datasets. Why the gap exists? What process produces invisible outgassing? What composition or structure allows an object to shed mass undetectably? These questions remain open. 3I Atlas, if it is indeed a dark comet, becomes one more example in a growing list. One more piece of evidence that the boundary between active and inactive objects is not sharp, that intermediate states exist, that the universe has no obligation to produce only extreme examples. Most comets are not spectacularly active. Most asteroids are not completely inert. Most objects exist somewhere between, shedding small amounts of material, exhibiting subtle activity, refusing the clean categories that make cataloging easier. The catalog adapts. New columns are added to databases: non-gravitational acceleration magnitude, detection confidence, spectroscopic limits on gas production. Objects are flagged as ambiguous, their classifications tentative, subject to revision as more data accumulates. 3I Atlas receives its flags, its uncertain status, its place among the objects that do not fit. Only took until the 21st century to notice that categories leak. Only a few dozen examples so far, out of hundreds of thousands of catalogued objects. Only a matter of time before the exceptions become common enough to redefine what is typical, what is expected, what deserves to be called normal behavior for objects drifting through space, warmed briefly by a star, watched briefly by observers who are just beginning to realize how much they do not yet understand. Observational limits are not failures of instruments, but boundaries of physics, thresholds below which signal becomes indistinguishable from noise, where photons arrive too infrequently to build up meaningful data, where the universe withholds information not out of intention but out of simple arithmetic. Every telescope has a limiting magnitude, a faintness beyond which objects cannot be detected no matter how long the exposure, no matter how carefully the data is processed. Every spectrograph has a minimum signal-to-noise ratio below which features cannot be distinguished from statistical fluctuations. Every camera has a noise floor, a background of electronic and thermal noise that obscures faint signals. 3I Atlas sits near these boundaries. At magnitude 23, the object is detectable, but barely. A single image shows it as a faint smudge, often confused with cosmic rays or hot pixels or background galaxies, until multiple images confirm that it moves, that it follows the predicted trajectory, that it is real. Photometry measuring the brightness requires combining many images, stacking them to increase the signal, averaging out the noise, extracting a measurement with error bars that are often 20% or more of the value itself. Spectroscopy is harder. Brightness measurements require only that photons arrive. Spectroscopy requires those photons to be spread across many wavelengths, each wavelength channel receiving only a fraction of the total light. For a magnitude 23 object, the photon rate is so low that even large telescopes with sensitive detectors struggle to collect enough light in any single wavelength channel to distinguish genuine features from noise. Exposure times lengthen. 10 minutes becomes 30 minutes becomes an hour. The telescope tracks the object, compensating for its motion across the sky, keeping it centered in the spectrograph's slit. The detector accumulates photons slowly, one by one, building up a spectrum that is mostly noise with hints of signal buried within. Data reduction software subtracts the sky background, removes cosmic ray hits, calibrates the wavelength scale, extracts the one-dimensional spectrum from the two-dimensional detector image. The result is a jagged line, fluctuating wildly from one wavelength to the next, the noise dominating the signal. Smoothing helps averaging adjacent wavelength channels to reduce the fluctuations, but at the cost of spectral resolution. Broad features can sometimes be discerned. Narrow features, absorption or emission lines that would provide definitive identification of specific molecules, are lost in the noise. Upper limits become the primary result. If water vapor were present at a certain level, it would produce a detectable signal. No signal is detected, therefore water vapor, if present, must be below that level. The limit is quantified, converted into a production rate molecules per second based on models of how cometary comas scatter and emit light. For 3I Atlas, the upper limits on water production are tight, implying less than 1 kilogram per second, possibly much less, at least 100 times below what 2I Borisov produced at similar solar distances. But upper limits are not detections. They constrain, but they do not confirm. The absence of detected water vapor means either water vapor is genuinely absent, or it is present at levels too low to detect with current instruments. The distinction matters for interpretation but cannot be resolved without better data, which requires a brighter object, which 3I Atlas refuses to be. Imaging searches for a coma face similar limitations. A coma, even a faint one, should appear as an extended halo around the nucleus, distinguishable from a point source by its spatial profile. Observers take deep images, stack them, subtract models of the point, spread function the characteristic shape a star produces in the telescope's optics, and look for residual extended emission. The images show nothing. Or rather, they show noise, fluctuations in the background, faint artifacts from imperfect image processing, but no coherent extended structure, no halo, no asymmetry that would indicate a coma or tail. Limits are calculated if a coma were present with a certain brightness and size. It would be detectable. No detection. Therefore, the coma, if it exists, must be fainter or smaller than the detection threshold. That threshold is not arbitrary. It is set by the brightness of the sky background light pollution from nearby cities, air glow from Earth's upper atmosphere, scattered moonlight, zodiacal light from dust in the inner solar system. All of these sources contribute photons that arrive at the detector alongside any photons from the target. The sky background is irreducible, at least from ground-based telescopes. Even the darkest sites, the most remote mountaintops, have sky backgrounds that limit what can be detected. Space telescopes fare better. Without atmosphere, without air glow, the background is lower. The detection thresholds deeper. But space telescopes are oversubscribed, their time allocated through competitive processes, proposals judged against hundreds of others. 3I Atlas, faint and unspectacular, does not rank highly. Time is allocated to other targets, exoplanets transiting bright stars, distant galaxies forming in the early universe, supernovae caught in the act of exploding. A faint interstellar object showing no activity competes poorly. Some observations are attempted, short exposures with Hubble, opportunistic images when the telescope is slewing between other targets, a few orbits of dedicated time when schedule gaps allow. The images confirm what ground-based observations suggested. 3I Atlas is a point source. No extended structure, no coma visible even with the superior resolution and sensitivity of space-based instruments. But even Hubble has limits. At magnitude 23, exposure times of tens of minutes are required for high signal-to-noise imaging. Only so many orbits can be allocated. Only so much data can be collected before the object fades further, receding beyond even Hubble's reach. The tyranny of brightness is not metaphorical. Faint objects are harder to study. They require more observing time to achieve the same data quality. They are more prone to confusion with background sources. They offer fewer photons, less information, narrower constraints, and as objects recede, they become fainter. Following an inverse square law, brightness decreases as the square of the distance. 3I Atlas, already faint at perihelion, dims rapidly as it moves outward. By mid-April 2025, the object has faded to magnitude 24. Only the largest telescopes can still detect it. Exposure times double. Spectra become impossible except with the most sensitive instruments under the best conditions. Observers submit proposals for time on 10-meter class telescopes, argue for the scientific importance of continued monitoring, request hours that could otherwise be used for more promising targets. Some time is granted. Observations continue. Sporadic, limited, extracting what data can be extracted before the object fades beyond reach entirely. Photometry shows continued slow fading, consistent with increasing distance, no brightening, no outburst. Astrometry refines the orbit, confirms the non-gravitational acceleration if it is real, measures the magnitude and direction with improving precision, though still with large uncertainties. By late May, 3I Atlas reaches magnitude 25. Detection becomes marginal even with the largest telescopes. Images show only noise with occasionally a faint hint of something that might be the object or might be a background fluctuation. Confirmation requires multiple images, careful analysis, statistical tests to assess the likelihood that a detection is real versus a random noise spike. The object crosses beyond Jupiter's orbit, heading into the outer solar system, destined to pass Neptune's orbit in a few years, then continue into the Kuiper Belt region, then beyond, back into interstellar space. Each day it moves farther. Each day it becomes fainter. Each day the difficulty of observation increases. By June, observations cease. Not because interest wanes, researchers would gladly continue if they could, but because the object is simply too faint. No telescope currently operating can detect it reliably. No meaningful data can be extracted from images that are dominated by noise. The photons arrive too infrequently, the signal too weak, the background too bright. 3I Atlas has faded into invisibility. Not gone, it still exists, still follows its trajectory, still moves outward at 34 kilometers per second, but unobservable. At least with current technology, at least from Earth's distance, at least until some future telescope with unprecedented sensitivity might, decades from now, Catch a glimpse of it in the far outer solar system before it departs entirely. Silence becomes indistinguishable from absence. The object that refused to outgas now refuses even to reflect enough light to be seen. The mystery remains unresolved, not because it is fundamentally unsolvable, but because the universe rations information, releases it only to observers with sufficient technology, sufficient time, sufficient proximity. Observers archive the data, hundreds of images, dozens of spectra, thousands of individual measurements of position and brightness, all stored in digital repositories, available for future analysis, for reprocessing with better algorithms, for comparison with future detections of similar objects. The data is finite, limited, but it is what exists. The total recorded knowledge of 3 Atlas's passage through the inner solar system. Papers are written. Conclusions are cautious. The object is classified as an interstellar interloper, inactive or dormant, composition uncertain, resembling a dark comet but without definitive evidence of outgassing, origin unknown, nature ambiguous. Recommendations are made for follow-up observations of future similar objects, for better instruments capable of detecting fainter signals, for space missions that could rendezvous with interstellar visitors if detected early enough. The catalog updates. Object 3I Atlas. Last observed June 2025, magnitude 25. Status unobservable. Trajectory well determined. Receding. Expected to remain within detection range of future facilities? No. Expected to return? No. Total observation arc 5 months. Total number of useful images 437. Total number of spectra 18. All low signal to noise. Conclusions minimal. Only visible for 5 months out of a journey measured in millions of years. Only bright enough to study for a fraction of that time. Only caught by chance during its brief passage through the inner solar system. Noticed by automated surveys that were not specifically looking for it, would not have noticed it a decade earlier before the surveys existed. Interstellar space is not gentle. It is not the frozen stillness that the phrase suggests, not a pristine void where objects drift unchanged through eons. It is an environment of slow violence, of radiation and particle bombardment, of chemistry proceeding at rates measured in centuries per molecular layer, but accumulating over millions of years into transformations that reach meters deep into solid ice. Cosmic rays arrive constantly, protons and heavier atomic nuclei accelerated to near-light speeds by supernova shockwaves, by pulsars, by processes still not fully understood. They traverse the galaxy at velocities where relativistic effects become significant, where a proton carries kinetic energy equivalent to the mass energy of multiple atoms. When such a particle strikes ice, it does not simply bounce off or embed itself. It penetrates, depositing energy along a narrow track, ionizing molecules, breaking bonds, creating a cascade of secondary particles that spread the damage across a small volume. A single cosmic ray affects only a tiny region, perhaps a few cubic micrometers, but cosmic rays arrive continuously, billions per square meter per second across the entire spectrum of energies. Over 1 million years, every cubic centimeter of surface material is struck thousands of times. Over 10 million years, the bombardment reaches depths of 1 meter or more, depending on the material's density and the energy distribution of the incoming particles. The effects are cumulative and complex. Water ice, when struck by cosmic rays, does not simply vaporize. The energy breaks apart H2O molecules, creating hydrogen atoms and hydroxyl radicals that can recombine in various configurations. Some recombine into water, some form hydrogen peroxide, H2O2, a more oxidizing species than water, less stable, but stable enough in the cold to persist for millions of years. Some form molecular oxygen, O2, trapped in the ice matrix. Some hydrogen escapes entirely, diffusing out of the ice and into space, leaving behind an oxygen-enriched residue. The ice becomes chemically altered, its composition shifts, its properties change. Pristine water ice is transparent to visible light, white or slightly bluish in reflected sunlight. Irradiated ice darkens, taking on a brownish or grayish tint as radiation-damaged molecules create color centers, defects in the crystal structure that absorb light preferentially at certain wavelengths. The crystalline structure itself degrades. Pure water ice forms hexagonal crystals, an ordered lattice where each molecule occupies a specific position relative to its neighbors. Cosmic ray impact